we're going to be specially interested in homogeneous systems of linear equations. So a homogeneous system of linear equation is one of the form ax equals 0, where the right-hand sides of the equations are the 0 vector. For those systems, we're going to write down a set of fundamental solutions, and there will be one fundamental solution for each free parameter. So remember, a free parameter is a variable whose column doesn't have a leading entry. The fundamental solution for a particular free parameter will be the solution you get by setting that free parameter to 1 and all the other free parameters to 0. These things are important because we're going to see in the final chapter of Algebra 1 that any solution can be expressed in a unique way in terms of the fundamental solutions. So let's look at an example here, which is this row-reduced echelon form matrix here. We're going to look at the solutions to Rx equals 0. So R is not an augmented matrix, R is the coefficient matrix from the left-hand side. In our example, let's give some names to the variables here. So each column of R will correspond to a variable, so let's call them x1, x2, x3, x4, and x5. And you can see that R really is in row-reduced echelon form. So there are some variables whose column does not have a leading entry. And if we look at the columns, you can see that column 1, column 3, and column 5 have no leading entry. So variables x1 and x3 and x5 are free parameters, and there will be a fundamental solution for each of those free parameters. So x1, x3, x5 are what we call free parameters. So let's think about what happens when we do a matrix multiplication, like multiplying R into a column. So if we multiply R into a column vector, it has to be a column vector of height 5. So let's say we multiply it into x1, x2, x3, x4, x5, like this. So we learned about what happens when you multiply a matrix into a column vector like this when we first studied matrix multiplication. We saw that what you get is a linear combination of the columns of R. So this product will be equal to x1 times the first column of R. So C1 means the first column here of R. And then we would have x2 times the second column of R. So here is C2, the second column, and so on. So a solution to R times x is equal to 0 is the same thing as a linear combination of the columns C1, C2, C3, C4, C5, which is equal to the 0 vector. And if we want x1 to be 1 and x3 and x5 to be 0, so if we're looking at the fundamental solution for the free parameter x1, then that solution will just be to take x1 equal to 1 and all the others to be 0, since C1 itself is the 0 vector. The first column of R is just the 0 vector. So the fundamental solution for x1 equal to 1 and x3 equal to x5 equal to 0 will just be the vector 1, 0, 0, 0, 0. So first of all, if we take x1 equal to 1, x3 and x5 equal to 0, then that solution should be 1, 0, 0, 0, 0. If we want x3 to be 1 and x1 and x5 to be 0, then what we're looking for is values of x2 and x4 such that x2, c2 plus x plus c3 plus x4, c4 is equal to the 0 vector. But that's really easy if you just look at the columns here. So look at these columns c3 and c2. So here's c3. You can see that c3 is just 2 times c2. So we have an easy solution, just making x4 equal to 0, where we say that we take x3 to be 1 and x2 to be minus 2. So minus the thing which was at the top of the x3 column. So when we have x1 equals x5 equals 0 and x3 equal to 1, then our fundamental solution will be that we take x3 to be 1, x1 and x5 to be 0, and we can have x4 equals 0 and x2 to be minus 2. And finally, if we want the solution where x5 is equal to 1 and the other free variables x1 and x3 are equal to 0, again, what we're looking for is a way to express the fifth column, this one here, in terms of the other columns. And you can see really easily that this final column, 3, 4, 0, is just 3 times the second column plus 4 times the fourth column. So that gives us a solution where we have x5 is equal to 1, x1 and x3 equal to 0, and then I need a minus 3 right here and a minus 4 here. So it's actually very easy for us to write down these fundamental solutions just looking at the columns of R and thinking, how can we write the column corresponding to one of our free parameters as a linear combination of the columns to its left. And in fact, what we can see is that we can use the columns corresponding to the non-free parameters, the variables which are not free parameters, very easily, because those columns are special. If a matrix is in row-reduced echelon form and a column contains a leading entry, then that column is really simple. It's just got a 1 in one position and zeros everywhere else. So it's very easy to use, for example, as column 2 and column 4 to add them to make column 5, because you can see that 3 times column 2 plus 4 times column 4 is very clearly equal to column 5 in our example. And that will work in general for any row-reduced echelon form matrix, because the columns which contain leading entries always have to have that special form where they've got a 1 somewhere and zeros everywhere else. So let's look at a construction for the fundamental solutions in general, so not just in the example we saw on the last slide, but in every case. On this slide, I'm going to give an expression for the fundamental solution to a homogeneous matrix equation R times X is equal to 0 when R is a matrix in row-reduced echelon form. So let's let our matrix R have ij entry A subscript ij and let it be an m by n matrix, row-reduced echelon form matrix. Now this will have some zero rows and some non-zero rows in general, so let's suppose that the non-zero rows are in rows 1, 2, 3 up to R, and then since R is a row-reduced echelon form matrix, the 0 rows have to come beneath this. We're now going to need some notation for which columns correspond to free parameters and which columns don't correspond to free parameters. So we're going to let Ci be the column which contains the leading entry in row I. So those are the variables which are not free parameters. And then we'll let D1 up to Dk be the columns with no leading entry. So those columns correspond to the variables which are free parameters. And you should notice that in this case we must have that K plus R is equal to n, because every column either corresponds to a free parameter or a variable which is not a free parameter. And there are n columns. So between them, the free parameter columns, of which there are k, and the non-free parameter columns, of which there are r, must make up the total number of columns, which is n. So all of this can be a little bit hard to follow, so let's just look at an example on the right of the screen here. So in this case, let's look at what all of these numbers would be in this special case. So this is my matrix R, and I have m equals 3, there are 3 rows, and n equals 5 columns, and there are leading entries in rows 1 and 2, so R here is equal to 2. On the other hand, the columns with no leading entry, there are going to be 3 columns with no leading entries, so K is equal to 3, and you can see that R plus K really is equal to n. So the column Ci is supposed to be the column of the row I leading entry. So the leading entry in row 1 is in column 2, so here we have that C1 is equal to 2, and the leading entry in row 2 is in column 4, so C2 is equal to 4. And the columns which don't have a leading entry, you can see here that D1 is equal to 1, that's the first column with no leading entry, D2 is equal to 3, because this next column with no leading entry is column 3, and the last column with no leading entry is column number 5. Okay, so that's what's going on in our specific example here. Now, the other thing I want to recall to your mind is the standard basis vectors. So remember that the ith standard basis vector, which we write as EI, like that, means the column vector which has got a 1 in position I and zeros everywhere else. And as I mentioned on the previous slide, the columns which are numbered CI, those are columns which contain a leading entry in a row-reduced echelon form matrix. So those are standard basis vectors. So we're now ready to write down our fundamental solutions. And there's going to be one fundamental solution for each free parameter. So in other words, there are going to be k fundamental solutions. And we're going to call the fundamental solution S1, S2, S3 up to Sk. So this thing here, this Sj, is going to be my jth fundamental solution. And remember that the interpretation of these fundamental solutions in terms of solving equations is that they're the ones that you get when you make the jth free parameter equal to 1 and all the other free parameters equal to 0. So then this fundamental solution you can work out is equal to E dj, so that is the djth standard basis vector, minus the sum from I equals 1 to r of ai dj times eci. So the ai dj, those are the entries in our row-reduced echelon form matrix R in column dj. So when I equals 1, you get the first entry in that column. When I equals 2, you get the next entry, and so on. When I equals r, you get the rth entry. And then all the entries below that are 0, because R has 0 rows below row R. So that's our expression for the jth fundamental solution. And let's just see what's going on in our example over here. We'll take the example of this matrix R on the right of the picture, and then we have 3 fundamental solutions. So S1, let's work this one out. So S1 will be equal to E d1, so that's the height 5 column vector with a 1 in position 1 and zeros everywhere else. Then I have to subtract off something where I look at the entries in that column. So the AIDJs are the entries in the corresponding column of R. But all those entries are 0. So in fact, all we'd have here is just that the first fundamental solution will just be E1. Okay, next, second fundamental solution. So the first term in this fundamental solution is ED2, so that is E3. Then I have to sum up something where the terms in the sum get multiplied by the entries in the D2 column. So D2 is 3, so we're looking at this column. So what we get in our sum is minus 2 times EC1, so E2, and then nothing else, because all the other terms in that column were 0. Okay, and then the final fundamental solution, S3, well, I should take ED3, so that's E5, the column vector 0, 0, 0, 0, 1, and then I have to subtract off 3 times EC1, so that's 3 times E2, and then minus 4 times E4. Okay, so those are our fundamental solutions in this example. And if you want to write them out, for example, we're running out of space here, so let's just write out one of them. But for example, this one here, well, what would it look like? It's going to be 0, minus 2, 1, 0, 0. That's the second fundamental solution. One thing we can get out of these fundamental solutions is we can prove that certain matrix equations always have non-zero solutions. So if you've got a homogeneous matrix equation, that's a matrix equation of this form, then for sure it always has a solution, because the 0 vector will be a solution. But if you have a matrix A which has more columns than rows, so if n is greater than m in this case, then actually there must also be a non-zero solution to such a system of linear equations, or such a matrix equation. And the reason for that is dead simple. So in this case, we don't have enough leading entries for every column to have a leading entry. So there are at most m leading entries because we've got m rows and m is less than n. So there must be a column which doesn't have a leading entry. So that means there's a free parameter. And of course we get a fundamental solution for that free parameter. And of course that fundamental solution is not 0 because it's got a 1 somewhere in the fundamental solution.